Okay, so let's move on to the a very important chapter of histone epigenetics, that is histone lysine methylations. Right. So, like DNA methylations, RNA methylation, SAM is the only sole methyl supplier. Okay, methyl donor, S-adenosyl L-methionine. You can imagine the SAM biosynthesis how important in our body. So that means the SAM biosynthesis is dependent on the folate metabolisms. So the nutritional intake strongly influences the your methylation outcome, epigenetic info. That is why in one of the epigenetic phenomenon class also I said how nutrition can influence our epigenetic inform just through this alteration of the metabolites. That's very important. Yes, where this methionine, L-methionine is function as a methyl donor, and then where primarily two residues on histone protein, where I'm focusing on upcoming classes, lysine and arginine, and mostly I'm going to explain the topic on lysine methylations. If time permits, we will see in detail where about arginine methylation. But yeah, so the coming to the epigenetic functions, I will highlight the lysine methylation function in detail, writing, erasing, and then as well as reading functions. And then the outcome, I mean the byproduct from this methylation reaction, you have this S-adenosyl L-homocysteine, that is SAH. In fact, this is the competitor for this methylation activity itself, because this can simply bind with the catalytic packet of proteins, methyl transferases, as well as histone, DNA methyl transferases, as well as histone lysine methyl transferases. So excess SAH also is dangerous. That means cell has to regulate SAH level also should be carefully maintained. If it increases SAH, it can simply block the activity. How? It can go and bind to the active site of the protein, so which is not available for the attaching to the SAM. Right. So coming to the lysine methylations. So you can look at these lysine structures, and when this KMT, lysine methyl transferases, and then KDM, lysine demethylases. So the monomethylations and single methyl group added, and then you have see three methyl group can be added, right? That's why it's shown 3 hydrogen on here. And then the second methyl groups are added here, that is dimethylation, and then this is a trimethylation. So this is very unique. So on a single lysine, 3 methyl group can be added. So it can exert 3 methylation groups. So it, and each and every internal product, I mean byproduct, has a specific functions. So see, for example, it's not always true, but on some specific cases, monomethylation will have one specific functions, and dimethylation will have one function, and tri will have one functions, which I'm going to explain when I talk about each and every modifications. So by default, this and this you should consider. So this is Me0, right, and Me3. So if this is active, means this is by default opposite functions. So this is repress and this is active. I'm talking about in general, and K4 will be different story anyway. So this is how the methylation mark introduced on the lysines, on the histone proteins. And then this becomes an important docking site. Once the methyl group added, and it's become a docking site, and then various proteins can bind and then reads the functions, and then it can bring a different biological outcomes, as I always say. And then obviously the enzyme mechanisms, autoregulations, can control the levels, whether the mono, Me1 or Me2. So the autoregulation is very important. It's happening basically. And then the different mono or dimethylation have a differences in stability. So it's in connection with the non-histone proteins. Okay, not on histone proteins. Some non-histone proteins where it gets monomethylation have some functions in terms of protein stability, and dimethylation will have some functions. So that is the logic here. So no need to worry for in connection with the histone epigenetics. Yes, so the lysine can undergo for 3 methylation groups, and then these will each will have a different functions, and then it's become a docking site for the effector proteins, because the methylation does not bring any charge on the histone proteins, whereas acetylation does. Acetyl group addition, it brings a charge imbalance, right? It brings a negative charge. Methylation does not bring any charge. So then how does it execute the functions? It will execute the functions by recruiting a effector proteins. That is the only way the methylation marks are executing. So its functions are dictated by the effector proteins. So without a reader, acetylation can function without reader as well, but it also can, the readers are present for acetylation as well. But in this case, without reader, it will not even function. That is the point. The arginine methylation very unique. You see, this is arginine structures, amino acid structure. It can go for a mono and dimethylations, not a tri like in lysine, but this di is very unique. See, when the methylations are present in both the amino groups here and here, and this is symmetric in both the positions, but what is interesting is only one methyl group is added. So symmetric dimethylations on arginine. Whereas you look at here, on a single position, amino groups, your 2 methyl group can be added. It's very interesting. And that is asymmetric. That's a asymmetric dimethyl arginine, ADME. Asymmetric dimethyl arginine and symmetric dimethyl arginine. And till now it's not very clear. This also you can keep in mind whether in our cell do we have a 4 methylation group on arginine. As of now, there is no report, because when the 2 methyl group can be added here, why not here, right? And why not here one more? So these are all the combinations are not discovered, but because there is a limitation in the research tools, okay? Because how do you identify? If you recollect my Histone method, Histone epigenetic methods class, if you want to identify methylation mark, MALDI, you think about it, right? And then when you subject a MALDI, that will tell you mass, whether mono or di. But where does it present? Whether it's symmetric, asymmetric doesn't tell you. So the mass spectrometry, in this particular case, that is an issue. That methods doesn't allow us or doesn't tell whether the identified dimethylations or monomethylation on which positions. That's very important limitation, particularly in the arginine methylation story. So this is one of the important lacuna in arginine methylations. But how do people end up to know this? Right, that is symmetric. They use only antibody. So they synthesize the arginine with symmetric modifications and asymmetric modifications, immunize, make an antibody against the symmetric, asymmetric, then they'll identify. But that is more like qualitative, doesn't tell you exactly. Sometimes there is a false positive can come. This is the only approach as of now, and then all the conclusions what we have in the literature only based on this. So there is a strong technical limitations. As I said, it's possible, one has to think about it, whether the cell carries these 4 methylations, very interesting, one need to identify, and what does it do? All these things yet to be discovered in the arginine methylations. Okay, so keep in mind from now onwards for another few classes, Histone epigenetic classes, I'll be focusing highly on these 7 methylation sites, lysine methylation sites, very important epigenetic modifications. So this is tail methylations and this is a core methylation. I already explained what is tail, what is core many occasions. And the first mark which I am going to explain, that is histone 3, lysine 4, then histone 3, lysine 9, 27, 36. These are all on histone 3 tail, and then histone 4, 20. So these are the well characterized epigenetic lysine methylation mark on the histone proteins. Then I'm also going to highlight the two important core modifications, which is exclusively present only in histone core and extensively studied or reported its role in the epigenetic functions. Lysine 79 positions as well as lysine 64 positions. Then I will, after this detailed discussion about each and every modification, in this case I'm going to explain each and every modification because you will understand each and every modification is a unique. It functions differently, unlike histone acetylations, where generally wherever it's present it always gene activation. Here you see there is a differentiation. So one mark, its activations, of course majority marks in repressions, but its function varies, which I'll show you. Function means in terms of recruitment and positioning, that varies, and similar to this core as well. So schematically just to tell you, so this is nucleosomes, and then this is, let's assume two tail right now. Okay, this is H3 and H4. This is from this N-terminal tail. This is the fourth positions, and this is ninth positions, 4, 9, and this is 27th positions. Sorry, okay, 27 positions, and this is lies in 36 positions. And then in H4 lies in 20th positions. Okay, so these are the 5 tail modification I'm going to explain in detail. Its function, enzyme, how does it functions, distributions. I'm going to highlight very briefly on about each modifications. Of course, I'm not going to detail about a lot of mechanistic informations, but this information will be highly useful when you try to conduct histone epigenetic research. See, coming to this first mark, histone 3 lysine 4, this one, histone 3 lysine 4. It's only modification when it is methylation present on these positions. Keep in mind as a thumb rule, it is always gene activation. The nucleosome carrying these methylation mark at these positions, that gene is always active. See, that means this mark you can easily expect it always works along with the HAD proteins, because that is also gene activation mark. And it play a very important role during cellular differentiations, which I'll show you when I talk about histone polycystate later. And this marks histone 3 lysine 9. Okay, I'm writing based on this positioning. And Me2 very important function, and Me3 is important function. It is repressive. So that means the nucleosome carrying this particular methylation mark at this position, that associated genes are always repressed. And similar to this as well, histone 3 lysine 27 Me3, very important gene repressive mark. And most of the inactive X chromosome that highly enrich this mark, you will understand and explain. And in acetylation class, I already said, these positions, when it is acetylated, it is obviously gene activations. But there is a unique function I already said. The enhancer DNA element containing nucleosomes always carries this. So in fact, this histone 3 lysine 27 acetylation is a mark for an enhancer element. So most of these enhancer DNA sequences and its nucleosome carry these particular acetylation marker at these positions. Enhancer is for gene activation, gene activating sequences, right? So you can easily connect. Still, it is a gene activation functions. And coming to the 36, very important, highly conserved mark, histone 3, lysine 36, Me3. Initially, they thought, many researchers, they thought it is a gene activation mark, but majority studies later confirmed it is basically a repressive functions. But why they thought is a gene activation, I'll show you the examples that I will understand. Okay, so this 4 on histone tail, histone 3 tail is clear. Now the one more modification on histone 4, that is histone 4 lysine 20, highly conserved across the eukaryotic species at these positions. So this is all canonical histone epigenetic mark, more or less conserved. This position mark conserved across the species, across the eukaryotic organisms, and in general, all these things are what I'm going to say. It's repressive, means in human repressive, means yeast also it is repressive. In Drosophila also is repressive. This is activation in human, means in a Drosophila also it is activations. Okay, so that is how it functions. The repressive activation function is more or less similar across the eukaryotic organisms. And then coming to this, only one very strong histone methylation mark on a histone 4 lysine 20, and that is gene repressive mark. It's also very unique. I'll explain when I talk about this particular mark. Okay, this is a 5 major histone epigenetic mark. This is very good information, good enough for a to become a master in histone epigenetic connections. Then 2 more marks I'm going to talk about it. That is lysine 79 and lysine 64. This is in a core regions. Okay. Keep in mind, so these tail modifications, it always functions by recruiting an effector protein. So that means if the methylation markers happens here on in the cell, this will recruit an effector proteins to make more repressive. So that is why this is the repressive functions. Okay, so it brings a repressive complexes. And similar to the K27, I mean K27 also almost same. So the K4, it also does, it brings the active complexes, right? And this is how tail functions. But the core, interestingly, doesn't depends on the reader. It directly influences the histone assembly, histone interaction, histone DNA interaction. In this case, you have DNA. So when the mark is present near to the where you have the histone and DNA is wrapping on the histone, when this methylation mark is added, but obviously that brings us some kind of steric hindrances, and then wrapping is disturbed. So in that way also this methylation at these positions can influence us. With the 2 examples, but there are many modifications also identified that play an important role in assembly of the DNA histone interactions. Doesn't bring a charge imbalances, but it can simply influences the wrapping, right? So this is the major things which I'm going to discuss in the upcoming classes, right? So the first mark, the histone 3 lysine 4 trimethylation mark. That's why I thought I'll show you the chip sequencing so that you'll understand how this distribution happens. So these are all these the distributions and related to the mRNA expression basically of the particular gene which they studied. So you see the more the expressions, in this case in the red color, see higher the occupancies, this particular mark on the just upstream to this. Of course, it's present in the gene body as well, but it just start picking up from this year onwards. So it's strongly linked to the gene activations. Right. So this is a crowded slides, but I'll just show you on a. This is an example for these active genes and one of the case in inactive genes. You see here, wherever this K4 trimethylation mark enriched, this case, okay, and then you see this The repressive mark is absent here. Monomethylation peaks bit bad here, but you see this is also absent. So it's a contradictions. It's bit, you have to read bit carefully. Just for I want to just given your attention how these marks never coexist, active and inactive marks. And this particular position you see when this is the peak, basically abundance. If you recollect my chip sequencing class, you will understand when chip sequencing experiments. So the peaks are abundant here. That means the marks are more here, the K4MA3. And the same position you see these trimethylation marks basically absent, right? Here absent, here also absent. The monomethylation enriches here. Monomethylation of K9, it's relatively kind of activation mark. K9 is 0 mark. Me1 is kind of near towards the activation mark. So I will just show you, then you'll understand in this case. Towards these directions, either this one or this one, in this case repressive. The monomethylations towards activations, because only single methyl group. But this is again context specific, not always, because most of the defined activation or repressions either will have the trimethylation mark or zero methylation. In very rare cases, mono or di, that will have a di means closer to the repressive in this case, and then here closer to the activation. That is why when they conducted a chip sequencing on the mono, they could see more on these matching to the activation mark. That is the easiest explanation why K9 trimethylation single methyl groups are enriching. Okay, right. So this is how you should read, and then there's a based on these only. In fact, after all these after that there are many studies are confirmed. Yes, these marks is always activations, and then these marks always repressions. You see, that's again for informations. The distribution of these K4 trimethylation mark mostly on the promoter abundance and the active genes, and then K9 distribution, it is also on the repressive genes in abundance, but coming to this closer to gene body, it's decreasing. And then the 27 is slightly different. It is also abundant, but it's unlike K9, it has throughout the gene bodies repressed. You see, each and every modification, its distribution is different. That means it has different functional outcome. That is very interesting. This was the reason why people they thought it is a gene activation. You see, it start increasing along with the gene body, but there is a different function for that, which I'll show you later. And then the K20 trimethylation mark, its distribution more in these towards the promoter, and then close gene body, it's decreasing. You see this and then this almost similar pattern, because in many genes these two marks coexist. That means K20 of H4, K9 of H3 trimethylation mark are always present together. Okay, so before I start explaining S3K4 trimethylation mark, I'll briefly introduce the enzymes. So most of the methyl transferases, all the positions, these positions, 27, 36, K4, all are done by methyl transferases. Histone lysine methyl transferases, or protein lysine methyl transferases. So there is one common feature for these proteins. These proteins carries a specific domain called Z domain. There is a unique feature for this histone lysine methyl transferases. All the histone lysine methyl transferases, you take it either these positions methyl transferases, this methyl transferases, because each and every position there is a different methyl transferases. Unlike acetylations, the same hat can acetylate multiple lysines, but here enzymes are evolved for each and every positions. That's very interesting. So all the methyl transferases carries the Z domain. The Z is name derived from this ZUFVAR enhancer Z trithorax. These are the different genes identified from the Drosophila. When they do the knockout of the Drosophila, each and every genes, And then they found there is a commonality in the domain architecture. They named, okay, these are the proteins carrying these common domains. So the set name derived from these basically. And all these set domains, the specificity varies, whether the K4, K9 or K27, 36, the specificity varies, depends on the complex that I will show you later. But it all carries some kind of common catalytic motif, that is this one. For information, it should have this NHS, very important motif for the histone lysine methyl transferases. It is a motif conserved in all the, irrespective of these active or repressive histone lysine methyl transferases. This motif is essential for the methylation activity. Right. So with this, I'll stop it up. We'll continue our classes about the H, because from now onwards, I'm going to talk about this histone 3 lysine 4-trimethylation mark. Okay. So this is the basics so far what I explained.